Hello everybody, Adam Lusek here, and today we're going to go over setting up an LLM-based financial assistant. So essentially at the end, we're going to have an LLM that can both query and respond to and give you insights into financial data. We're going to cover four main sections in this video. The first will be getting a local instance of Llama 3 up and running, and then actually fine-tuning that on a Form 10K question and answer paired dataset. We're then going to set up the data pipeline to grab relevant Form 10Ks from a ticker symbol from the SEC database and the SEC website. The third part is then going to be getting that information that we grab from the pipeline, using another local embedding model and an in-memory vector store to create a really rough vector database that will allow us to query it and get the relevant context that will be required to actually answer the question from the Form 10Ks. And then we're going to combine it all together to create a very simple financial analysis retrieval augmented generation flow. Essentially, that's going to take our query, get the context from the Form 10Ks, pass it off to our fine-tuned language model, which will then do the analysis and return the response. In the spirit of keeping everything educational and open, we're actually going to do this all fully from a Google Colab notebook. So regardless of whether you have a good computer or not, you can follow along and actually do all of the same things that we have here completely free using the free GPU that you can get with a Google Colab notebook. So this will be linked down in the description below, and you can actually follow along and run all of these as I'm doing it yourself. No need to pay anything, no need to set anything fancy up. All that you're going to have to do is to change your runtime to the T4 GPU in the top right corner. It's going to say connect to a runtime here. You're going to go to additional connection options, click on change runtime type, and then you're going to click on the T4 GPU. I have a pro version of the Colab, so I have access to a few other GPUs that I can use, but you'll get free access to the T4 GPU for a limited amount of time to test things out. For this video demonstration, I'll actually be connecting to the more powerful L4 GPU, but the T4 GPU is perfectly adequate to run everything in this notebook, including all of the fine-tuning, all of the local models, and all of the inference that we'll be doing later. But once that is connected, you're good to go and ready to start. All of these first three boxes that we have here are installing all of the packages that we'll need and then importing them all, as well as a couple API keys that we'll want. So as I run this, what you're going to also need is your Hugging Face token. So when you go to your Hugging Face account, it's going to pop up here in your access tokens in your settings. And so this is actually going to be useful for being able to load gated models. And so Llama 3 is a gated model, and that Meta asks that you provide some information before you're actually able to download that. So all you'll need to do is copy this, add this into the field here, and then you'll be able to download Llama 3. Additionally, we'll be using the SEC API package to make things really easy for actually getting the Form 10Ks later on down the line, and you can get a free API key here. It'll allow you up to 100 calls of the API per day, and that's more than enough for what we need to do to load. Each time we load a Form 10K later on, we're actually only going to call the API 3 times. So you shouldn't run into too many issues for just testing usage here. All you need to do is go to this link, secapi.io, click on Get a Free API Key. You can log in with Google, and they'll give you a free API key to start getting started with right away. Super easy. So I'm going to go ahead and populate mine and run these first 3 dependencies. So now that we have the packages installed and everything taken care of and imported, we can get started. So part 1 is actually going to be loading the language model and then fine-tuning it on our data set that we want to make it very much more specific to answering financial-based questions. And so to do this, we'll be using Llama 3, and to do the fine-tuning, we'll be using the Unsloth library. So Llama 3 is a language model from Meta that is an open source language model, meaning that we can import it from something like Hugging Face, and it has open weights that we can use. And for this example, I'll be using Meta Llama 3 8B Instruct. And so as I mentioned before, this is a gated model. So when you go to this actual website here, you're going to have to just put in some contact information, and then pretty much almost instantly they give you access to this stuff. And this is what we'll be using. As for Unsloth, Unsloth is a really cool open source library that is all based around fine-tuning specific open source models. And so they essentially just make it super easy with a lot of their packages to do these parameter efficient fine tunes without having to know, too much of the underlying architecture of actual language models and how to sort of attack, transformer models to do the fine tuning yourself. they cover a lot of this and have some really good documentation and some really good examples that you can augment for your own use case, which is what I actually did here. So if you're interested in something a little bit more custom, definitely check them out. Check out their repo and their website. But let's go over how we're actually going to be using it and loading and fine-tuning our model. So to do this, we're going to first load the model and its associated tokenizer. If you're unfamiliar with how models and tokenizers sort of coexist, essentially the model, the language model itself, will only be able to process numbers. And the tokenizer is what can take and translate English text or any sort of language text into those tokens that the model can process. And then vice versa, it can take the tokens and translate them back to English text. So this is a step that happens every time you query a language model and you get English text out. Your query will go through the tokenizer, be turned into numbers. Those numbers will be processed by the model, and then the model's output will be numbers, which go back to the tokenizer, which gets translated into plain English. So we need both to be able to operate on this local model. And using this, we're going to first path to the model. We see that it's meta-llama 3 8p instruct. And I got that from right here. So if you go to a Hugging Face model, you can click on use this model, click on transformers, and it'll show you a quick pathway right there. And so that's what we'll be doing. And because it's gated, we're going to have to pass in our Hugging Face token, which we defined above. The other three things that we have here are getting a little bit more specific into the internal calculations of how these models work. So I'm not going to go too in depth as to what each one of these does. But as a sort of high-level overview, the max sequence length is going to be the maximum number of tokens that a model can actually process in a single pass. And so for this, we've set it to 2048 tokens. You can think of this almost as kind of like a context window. The data type for the model then is we're going to set it to none, which means it'll auto-detect based on the hardware. And for the Tesla T4, that's going to be float 16. And float 16 essentially just means sort of the number format of all of the numbers being processed within the language model itself. Of course, the longer the number, like a float 16 or a float 32, the more precise these weights can be during the training. However, the more computation you actually need. And so similarly, load in 4-bit means that we're going to do 4-bit quantization. And what quantization essentially means is we're going to take the weights of the model and all of the sort of numbers and then smush them down a little bit into more simplified numbers so that we're going to lose a little bit of accuracy from actually making the numbers a little bit simpler. However, this generally works still well because you can actually save a lot of the memory usage with processing these numbers. And then also the actual numbers themselves don't matter too much for the generalized sort of processing of the language model. So none of that made sense. No worries. We'll be going over a little bit more of these because we're getting pretty specific into fine-tuning, but not going to get too super into it. And I have a lot of other different things and comments here to try and sort of tell everybody exactly what's going on with each of these and why we need them. But we're just going to run this, and you're going to see that it's going to start downloading the Llama 3 8B instruct model, which is about 5.7 gigabytes. So we'll wait for that to download and be right back. So now that that's all loaded and we have our lovely little sloth friend here, we can actually start adding on what we're going to need to actually do the fine tuning on our data set. And so to do this, we're going to be using LoRA adapters, which are essentially low rank adaptation parameters. And so LoRA, or low rank adaptation, is a technique that's used in sort of machine learning to fine tune these large language models that have a lot of parameters a little bit more efficiently. Researchers have found out that if you actually add an additional set of smaller parameters to an existing model, what you can do is then run the fine-tuning on those new sets of parameters that you've added, and it'll affect sort of every single calculation down the line and give a noticeable difference in the actual output. And so instead of having to spend all of the processing power and all of the compute to take this 8 billion parameters, what we can do, or 8 billion parameters of Llama 3 that is, and retrain everything from scratch, what we can do is just introduce a few of our own smaller parameters, run our fine-tuning on those smaller parameters, and that will have enough of an effect on the overall computation going on within the language model to actually have a noticeable effect on the output. This type of fine-tuning is called parameter-efficient fine-tuning because we don't actually need to retrain all of the language model, just a few parameters here and there to get the noticeable effect. So what we're going to do, and in this function here, using the fast language model get parameter efficient fine-tune model, this is where we're actually going to add in those extra parameters so that we can try it out and fine tune those parameters. Essentially, we're going to pass in the model, which we originally defined up here with from pre-trained. So that's going to be, of course, llama 3 8B instruct. And then we're going to go over just a bunch of sort of different things of how these extra parameters should look and where these extra parameters should fall. So once again, this is getting really specific into sort of the training and the calculations that actually happen internally within language models. But to give a quick one-liner of each of them, R of 16 is going to be the rank of the adaptation matrix. And so pretty much all of the calculations that go on within language models are based on matrices or tensors and multiplying them all together and doing some other fancy things there. But essentially, we're going to have a rank 16 matrix, which is going to be a bit more of a small matrix in comparison to the parameters that are actually within the llama 3 model. We're then going to specify which layers to add these adapters to. And so that's going to be all of these here. And so I have a nice thing down here that actually tells you what each one of these will be. So Q is like the query vector, K is the key vector, V is the value vector, etc., and so on. We're also going to add in a scaling factor for these adapters and for these parameters, which will control a little bit of the weight. And so what I have here, it's a scaling factor, controls the impact of the adapter on the model's outputs, typically set to a small positive integer. And so just to pause in the middle of this, essentially all of these parameters are all sort of different things that a lot of researchers are trying to find sort of the optimal combinations of when they're making these huge language models like llama 3. So what we're doing here is a little bit arbitrary. I took most of these actual numbers from some existing Unsloth documentation just to have somewhere to start, but they can almost all be changed and get sort of different results. So that's also something fun that you can test out with. But we also have some stuff for dropout rate, which is another sort of training method, bias handling, gradient checkpointing. And of course, I've got more down here that explains what each one of these are if you're interested in. But if you're not and just want the TLDR of it, all of these are just different ways that the calculations are going to be affected while doing this fine tuning on the weights of the model itself. So what we can see when we actually run this is that we are going to add, yes, we've patched 32 layers with 32 query key value layers, 32 zero layers, and 32 multi-layer perceptron layers. So perfect. Looks like we've added all of these. That is great. And then now that we have all of the parameters ready that we're going to be doing the actual fine tuning on, we need the data and the data set that we want to do this fine tuning and training over. The data set that we'll be using is this. It's the llama 3 8B financial QA data set that Virat Singh here actually posted just a few days ago. And it's going to be in a perfect format for what we're going to be using, because essentially he's generated 7,000 rows that have a question, an answer, and then the context retrieved from a Form 10K of what was used to generate that answer. So essentially, we're going to take this and format it nicely so that we can train all of these parameters on this expected prompt, and then it should essentially be able to get our final fine-tuned model a little bit better at doing a task like this. So hopping back over to the notebook, that's going to look a little something like this. We first need to define the prompt, and all of these things in brackets are actually going to be special tokens that are very much specific to llama 3. So you can see that it has some things like a beginning of sentence token, end of turn token, end of sentence, end of text token. And these are all very, very necessary in a prompt, especially with llama 3, because this is how it's going to understand what's what, what's where, similar to when you write like a system prompt for an OpenAI model, and then a user message and an AI message. Using these special characters in a full just text-based prompt is how we're going to specify that. So for our prompt, we're going to have the begin of text, which is our starting, begin of sentence turn, the system header, and my system prompt is just going to be simply below is a user question paired with retrieved context. Write a response that appropriately answers the question, include specific details in your response, end of turn. So that's going to be the system, and then I'm going to start with the user with a start header, and then we're going to have the question, which we're going to pass information through, the context, which we're going to pass information through, and then that's going to be another end of term, because that is what generally the language model in its final state is going to see. And then we start here with the assistant response. We just have response and then start header assistant. And so that will start generating and should be all right. So one of the things too is that this is all going to be formatted nicely for something that we can actually use to train. So what we're going to also need is the end of sentence token, which we can grab from the tokenizer, and that's going to be this end of text. And so why we're going to need that is because as we're putting in sort of the question, the context, and the response into this prompt, so the question, the context, and the answer from the data set, we're also going to want to add that end of text token to signify the end of this full prompt, so that when our final language model Llama 3 is generating, it will know that after it generates a response, it should add in the end of text token or end of sentence token. And so we just make a very quick sort of formatting prompts function that will take the questions, the context, and the responses, which is question, context, answer. That's from the data set here, and then map them all and create a training data set that will have this prompt properly formatted with every single line of actual information from the data set. So we're going to be using the datasets library to actually load that, and then just mapping it with this formatting prompt function. And so what that will look like when we run it is downloading the data set very quickly, mapping it all 7,000. And then if we just look at the text of the first piece of the data set, we can see that it's a fully nicely formatted string of text that we're going to be using for training. So we can see that it's all nicely mapped in the way that our prompt is supposed to be right here. If we take out the text, we can see actually the full line here that includes the original question, answer, context, ticker, and filing. That's right here in the data set. But then our text that we're going to be using is, of course, this down here. So that's great. Now we've loaded our data set. Time to train it. Quick note, actually, you can see that the end of text token was added on here. That's why we're adding on this here from the tokenizer. And we see that that adds perfectly well. Great. So now to define the trainer. And to do the actual training, we're going to be using a Hugging Face package, the Supervised Fine-Tuning Trainer, to do some transformer reinforcement learning. All sorts of fancy stuff, but essentially I've got this quick definition. Supervised fine-tuning is going to be the process in machine learning where a pre-trained model is further trained on a specific data set with labeled examples. So in this, we're going to have our pre-trained model, Llama 3, that's further trained on our specific data set, this Llama 3 8B financial QA that we've formatted correctly here, and it's all going to be labeled. So all of this is sort of just the labeled data that we're going to be using. And then, of course, these parameters that we're going to be updating are going to be the LoRA parameters that we added on up here. And so during this process, the model learns to make predictions or classifications based on the labeled data, improving its performance on the specific task at hand. This technique leverages, the general knowledge the model already has acquired during its initial training phase and adapts it to perform well on a more targeted set of examples. So Llama 3 is already a good general model, but we're sort of adapting it to do better on financial Q&A with these labeled examples here in the data set. And then, some of the other stuff that I've got here is just supervised fine-tuning is commonly used to customize models for things like sentiment, language translation, task-specific annotated data, which is precisely what we're doing here. So to do this, we need to define a trainer, and this trainer is going to be, very technical. This is all sort of stuff that is going to be related to the actual math and calculations that are going on behind the scenes to update the weights and biases of the internal model to help make the predictions more in line and more specific to what we're expecting from this financial data set. So the trainer takes in a lot of arguments, but most of the arguments are actually going to be just stuff that you don't necessarily need to worry about unless you want to get into the super nitty-gritty specifics of training neural networks. But the main things that you're going to want to focus on here are the model. And of course, the model is going to be what we imported up here, which is our Llama 3 8B. And then we added on the low rank adaptation adapters onto this, which is what's going to actually be getting trained during this. And then we pass that model down through here, pass in the respective tokenizer, path over to the dataset, which we just have as dataset here, and then path into the part of the dataset that contains the text data that we're going to be training on. So within the dataset, it has this text argument here in this dictionary, and that's going to be our nicely formatted information that we want to actually be fine-tuning on. So we put that there. And then max sequence length is just going to be the same as we set it up when we imported the model above. And then the rest of this stuff is pretty much just going to be around general arguments for actually just machine learning training. So I'm not going to go too far or too deep into this. I have a little bit of a follow-up for each one of these down here if you're interested in what each one of them is. And of course, maybe I can make another video that actually goes into the nitty-gritty of the actual calculations and stuff going on behind the scenes here. But the thing that you should definitely take note of is right here, max steps. So this is the amount of sort of times that all of these calculations are going to be ran and updated. Of course, the max steps can be a little bit arbitrary. Generally, in terms of machine learning, they use the term epochs, and epochs means sort of going over and training a model on an entire data set once. And so for this, I tried to run this and it was about 900 steps for one epoch, but for the sake of examples and to keep it sort of friendly for a Google Colab notebook, we're just going to be doing 60 steps here to show what this is. So you can look a little into what each one of these does if you're interested, but we're going to skip over this as a lot of this is just based on the calculations for training. So once our trainer is defined, we'll see that it will do all this, tell us that max steps is given, so it'll override the value given in number of trained epochs. That's fine because we have it commented out anyway, and then we'll be able to run the trainer. So you'll see right away that, there we go, we're doing it on one GPU, of course our L4 here, and then we have a 7,000 examples, and then we're going to do about 60 steps. So this step is sort of going to take the longest. On a T4, it takes about 6 minutes. On an L4, it's going to take about 3 minutes. So I'll be back once this is all done. But as you can see each step that we're taking and then the training loss, which essentially during the training of language models, it's trying to minimize the loss or this loss function to get better results. And so those results are going to be your expected output versus the output that you're generating right now. So in general, a lower loss means that you are more accurate in your actual predictions on the language model. So we're more accurate in getting the actual generated answers out that we're interested in from this. And so it'll go through, update all of those, give us this metric here, and then show us that. So I'll be back in a bit when this actually fully runs. So if you've been following up until this point, congratulations. You've now just officially trained a local model using a GPU completely all by yourself on a custom data set. So hopefully I didn't lose you too much in a lot of the nitty-gritty specifics of this, but essentially what we've done is trained the extra parameters that we added onto the model. So that was about 42 million parameters across 60 steps with our data. And so we can see that we went from a loss value of about 4.5 down to roughly about 1. So that's good to see. Any more might be, a little bit of overfitting. But 60 should be great for now. And so we now have a fully fine-tuned local instance of Llama 3. So that's super exciting. If you want to actually save this model locally, what you can do is use these functions to save them. So you're just going to have to click on this file button, and then you're going to want to mount your drive, your Google Drive. And then within that, you should create a folder, change the path of these, and then you can actually save all of the weights and stuff as actual files. And what that'll allow you to do is if you actually click on this one, you can reopen with all those saved files, redefine everything, and just use your model again. One thing to keep in mind is that for Colab notebooks like this one, if you don't save the model, it will get deleted. So you should probably save it if you want to use it later without having to go through the hassle of actually training everything all over again. But since we've got this up and running now from our training, and that's perfect, we can move on finally to setting it up to actually use. And so this is where we're going to be defining our inference functions. And so inference in and of itself refers to the process of using a ML model to sort of make those predictions and generate the outputs based on new and unseen input data, which is going to be the questions that we're going to be asking it later on down the line. And so this is essentially just going to be the chat function of actually putting in some text and having it respond with some other text. This isn't going to be too complicated. Essentially, we're going to run in the prompt, our fine-tuned prompt up here, which we have right here. We're going to pass in a question and the context. So the question is going to be our user query. The context is what we're going to get later on down the line when we get the relevant context from sort of our SEC documents and pass them into here. And so that's going to be added here. And then we're going to leave the final part blank, which is this response part. And so we're leaving that blank because that's where the language model will pick up and start generating. And so we are going to pass all of that into our model with the generate method right here, passing in all the inputs. We're going to define that we want to use new tokens or max new tokens of 64 so that it doesn't generate too much. And then we're going to have a pad token. So the pad token is set to the end of sentence token to sort of handle the generation so it doesn't run away. And then using the cache essentially means it's just a little bit of an efficiency thing so that it can reuse and doesn't have to, it can reuse some of the calculations that it's done earlier when generating these outputs, and it doesn't have to sort of do all of the calculations again at once. We then run the outputs through the tokenizer to get it into English words, and that gives us a response. So let's define this. And then I just have a very simple function here that we'll take because what we're going to get out is the entire prompt with all of the generation as well. So this is just going to take everything after the response and send it out to us. So let's try it out. The question we're going to ask is, what were the primary drivers of notable increase in research and development expenses for FY23? And our context that we're going to pass in is just going to be this line here that says, increase in research and development expenses primarily driven by increased compensation, employee growth, engineering development costs, data center infrastructure. And so let's run it through our few defined things and see what we get back from the language model. Great. So we see after a few seconds, it says increased compensation, employee growth, engineering development costs, and data center infrastructure were the primary drivers of the notable increase. Looks good to me. The full response that we actually got is, of course, what we're seeing here. So with all of the special tokens, and then that's where this function, the extract response, comes in. So it'll just grab just the last bit of text. So great. Now we have everything set up, our model fine-tuned, and then some functions for actually running it with questions and context with a prompt. So that's great. Now we need to set up the actual getting the context part of it from the SEC. This is going to follow a very simple retrieval augmented generation flow, where we're going to take the user question that we're asking, do a bit of context retrieval from the form 10K, and then inject that into the context part of our prompt here, along with our question, to have the language model respond. And so to be able to do this, we're going to essentially need to gather specific form 10Ks, parse and chunk the text in them, vectorize and embed the chunks into a vector database, and then set up a retriever to semantically search the user's questions over the database to return relevant context. What all of this lets us do is essentially take our question, and then it'll find sort of the pieces of the form 10K that most relate to the question that you're actually asking. And then we can use those pieces of the 10K as sort of guides for our language model to actually present a final answer to us. So sounds a little bit more complicated when you say, vectorize and embed, but using a vector database is how we're able to run these semantic related searches over the actual contents of the 10K. And so if you're not sure what a Form 10K is, it's an annual report required by the US Securities and Exchange Commission, or the SEC, that gives a very comprehensive summary of a company's financial performance. So let's get started on actually setting that up. As I mentioned earlier, we're going to use the SEC API that's just right here for a very quick and easy way to actually do this. And so what we're going to be doing is not actually grabbing the full Form 10K. For this project, we're just going to be grabbing the Form 10K Section 1A and Section 7. That's going to be the risk factors and the management's discussion and analysis of financial conditions and results of operations for a specific company. To do that, I literally just have this function right here that's get filings. So it'll take in a ticker. For example, Apple's is AAPL, something like NVIDIA's is NVDA. And what it'll do is it'll use the SEC API query API to find the right filing, the most recent filing that they have. It'll grab the URL of that, and then they have an additional extractor API. So we can pass in the URL, the section that we want and how we want it in. So we want section 1A, section 7, and the text of them. And so it'll grab those as text, and then we're just combining it together here and returning the combined text. So all this is doing is taking in the ticker, finding the form, grabbing those specific sections, the text of the sections, and then just spitting me back out a super long document that includes both section 1A and section 7 in raw text format. To be able to actually run semantic retrieval, so when you ask the question to get the relevant parts of what we've gathered from the Form 10K, that would be context required to answer your question, what we need to do is set up that vector database. And to do that, we're going to need to use some very fancy things called embeddings. And so we're also going to use a local embeddings model, the Beijing Academy of Artificial Intelligence's Large English Embedding Model, version 1.5. But quick overview on what embeddings are. They're pretty much just numerical representations of data, typically used to convert, complex high-dimensional data into lower-dimensional space. Sounds very complicated. Essentially what it does is it's going to take a word and turn it into just sort of a vector or just a bunch of numbers. And these numbers are essentially, through the training and through the machine learning process and learning process of these embedding models, these numbers are going to be representative of different sort of the meaning of the word in number form. So this is a very, very abstract way of actually thinking about information. But these embedding models are able to take our word, transform them into numbers, and then those numbers essentially encapsulate the meaning of the word. And so what you can do is then you can run calculations on numbers. So you can find numbers that are very similar, and essentially they'll be pretty much semantically similar. So you can retrieve similar numbers of things, and that'll give you the different entries in the database. And this is a long way of saying that you can essentially just find things that are similar to what you're asking. So in this case, the question that we're asking, we're going to try and find sort of similar sections, similar parts of text from these sections that relate to that question so that we can use it as context. But long story long, let's actually load that. So we're going to be using, of course, this open source model. So it's from the Beijing Academy of Artificial Intelligence. It's just a generalized English model for generating embeddings. All we're going to do is path to it here. We're saying that our device model is in CUDA because that is what GPUs run with. We're going to do a little bit of normalizing. Don't really need to get too into this, but passing that all into LangChain's Hugging Face embeddings function here, we can download and load the model. So we see that the model itself this time is about 1.34 gigabytes. Google's data centers are working overtime to download that at 300 megabytes per second. So that was phenomenal and great. Now we have these embeddings. And so what we need to do is actually pass the embeddings along with parts of the text into our vector database so that we can run this. And so this will go through essentially these 3 steps. We're going to split up all of the text that we got from the Form 10K here. We're then going to vectorize it using our embedding model, and then we're going to have to set up that retrieval function. A little bit of a breakdown on what all of these do. So text splitting, it's the process of just breaking down a large document or text into smaller, more manageable chunks. We'll go into how that happens a little bit later. And so this is very necessary because essentially we can't put, these Form 10Ks are long. We can't put all of it into the language model prompt because the prompt at this point can only accept about 2048 tokens. And so these things can go upwards of millions of tokens because they're super long reports. So what we want to do is just find the relevant part, pop it in as context, and then go on our merry way. To do this, we have to put them all into a vector database. So it stores these data in the forms of vectors, which are generated by the embedding model. And those are the numerical representations of the text, images, etc. And the vector database that we're going to be using here is Facebook AI Semantic Search. Super easy, lightweight library. You can do it in memory, which means that you don't have to actually save any of the information being processed onto your disk, and it'll be perfectly fine for our demonstration purposes here. So how the split documents and embeddings work together. When text data is split into smaller chunks, each chunk is then converted into those numerical vector, the embeddings, and using this embedding model, which in our case is going to be the BGE Large English Version 1.5. And then we're going to store it in our vector database, the semantic search library that we put up. And so it stores these embeddings along with the references to the original text chunks. So we'll essentially have the chunk of text and then the created embedding. And then What this allows us to do is index the vectors for super fast and efficient similarity searches, as I've been trying to get at a little bit earlier. And what this allows us to do is that when a query is made, the vector database searches for the most similar vectors or text chunks to the query vector, retrieving the relevant text chunks for us to use based on their similarity. So, long story short, it's actually not a lot of code here at all. So we're just going to be taking in what ticker we want here to actually do that. We're going to grab the filing data with the get filings function that we defined up above, and then we're going to split it. So to do this, we're going to be using a recursive character text splitter, which is essentially going to take, using the length, 1,000 characters, create a chunk, and then the overlap is going to be 500 characters. So 500, it's going to go back 500 and then go another 1,000, take a chunk, go back 500, do another 1,000, take a chunk. And essentially for this, it's going to create about 160, 145 or so different chunks of text that we're then going to split with this text splitter and then pop it into our vector database, the Facebook AI semantic search one. Super easy using this method. We just pop in the split data along with the embeddings that we generated from our model up here, embeddings. So that'll path towards our embedding model. And then that creates our database. And so then LangChain has a really easy way of actually being able to use this as a retriever with just doing the database as retriever method. And then that creates your retriever object. So you can pass natural language queries, and we'll get to that a little bit later in the next step to get the relevant context. So let's go ahead and run this. And for the example, we'll just use Apple. So, get filings is not defined. Forgot to run that. Perfect. Now that that's ran, this should be able to work now. So let's pass in Apple. It'll get the filing data, initialize the vector database, do all the chunking, and do it all great. So that's all done. Now we need that all of the chunks of the data and all of the embeddings that we're going to be able to search over are put into the vector database. We need to set up the way to do the retrieval. So retrieval is essentially just, as we've been saying, process of querying a vector database to find and return the relevant text chunks. And that takes sort of the form of this. We're going to pass in the retriever, and the retrieved documents are essentially going to take in the query, which might be, for this example, how have currency fluctuations impacted the company's net sales and gross margins, and then return all of the documents that it believes are going to be relevant towards that question. So let's actually run this and try it out. So what we can see is from our question here, this is all of the context that it's going to be providing. So it says the company's financial performance is subject to risk, yada, 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 company's primary exposure. And so all of this is coming from the actual Form 10K and is sort of everywhere where it's similar enough to our question that it believes that this context could be used to help answer it. So now we have that all embedded. We have all of the context. The last part is actually just stringing it all together. And so this is where we're going to actually put everything together. And so hopefully the rest of this didn't confuse you too much, because it's super simple here at the end. All we're going to do is take in the user's question, which is just going to be this simple input here. We're going to retrieve the documents using what we just did, the retrieve context. And then we're going to pass the question and the context into our inference function here, which if we go back to the inference function, all that's going to do is put the question that we had asked into this prompt, add the context that was retrieved into this prompt, and then start the generation from the language model here. And so from that generation, then we're just going to extract just the response and then print it out. So I have a few example questions down here that we can try out. What region contributes most to international sales? Let's see what it comes up with. So it grabs the context. It's now generating the response. It says that the Americas region contributes the most to international sales. Not sure if that's 100% true. I believe Apple's, based in the Americas. So let's try something different. Where is outsourcing located currently? And so it'll go through, and as we can see down here, that it's running a whole bunch of generations. It says outsourcing partners are primarily located in China mainland, India, Japan, South Korea, Taiwan, and Vietnam. Cool. Let's ask, does the US dollar weakening help or hurt the company? And it comes up with none. So never said that these were great, but it's interesting to see. It apparently wasn't able to get enough of the information to actually make a confident answer there. So no worries. Let's ask what significant announcement of products happened during fiscal year 23. So it returns, Apple announced the following significant products: iPad and iPad Pro, Apple TV, MLS Season Pass for Major League Soccer. That's cool. That's great. Finally, let's ask, iPhone net sales. See what it comes up with there. It says that the iPhone net sales decreased 2% or 4.9 billion during 23 compared to 22 due to lower net sales of non-Pro iPhone models, partially offset by higher net sales of Pro iPhone models. That's perfect. I know that to be a fact. So essentially, we've trained our whole language model on a financial Q&A dataset, set up a data pipeline, 2 SEC Form 10Ks, done some vectorizing, chunking, and getting context retrieval out of that, and then combining it all together to do this Q&A. So as you can see here, it wasn't the best at actually answering truthfully a few of these, and there's a lot that could go on to that. The first is that we didn't really fine-tune this model a lot. It was just 60 steps on about 40 million parameters, which in the grand scheme of models and the 8 billion that it has is not too much. We've also loaded this model in 4-bit quantization, which means that it's going to lose a little bit of its actual accuracy when running the inference. So this is already a very small model, but we're running it even smaller to make things a little bit more efficient here. But still, it was able to accurately say a few things here. Some of my thoughts that I had is that this really shows just how much, processing is needed for training and running very large advanced language models. As you can see, there's some latency here, and it takes still a while to just train about like 40 million parameters. Now imagine doing that with a data set of, trillions of tokens across upwards of like a trillion parameters for the super large like GPT models. It really puts into scale what the average consumer like you and I are able to do versus sort of those big powerhouses like OpenAI, Mistral, Anthropic, and whatnot. And so, but even with all this time and effort put in, small models can be very powerful and doing sort of cool stuff like this. So hopefully this was a really good educational way to sort of explore how to actually set up local models, set up local embedding models, do parameter efficient fine tuning using the LoRA method, and then also setting up a simple RAG flow. As mentioned, all of this is doable completely from a Google Colab network. So go ahead and try it out yourself, tweak some of those parameters, try things, see what works for you, see what might work better. A lot of the stuff that you can actually tweak are things like, the context splitting. You could use a different text splitter, you could use a different vector database, different ways of doing that. You could fully change the actual embedding model. You could fully change pretty much any of these super specific ways that the actual training is calculated here, doing more step size, doing it maybe on an epoch or two, stuff like that. You can also just change sort of the model in and of itself. Right now we're using Llama 3 8B Instruct, but you could pretty much change this with any sort of open source model that Unsloth actually supports. So hopefully this gave you a lot of good ideas around building out these sort of local open source different applications, and then also sort of the ability to run these calculations and also run sort of a lot of these fun different pipelines and putting together stuff all together and having a deeper understanding of what's actually going on behind the scenes when language models do get trained and how they work a little bit closer at an open source level.